Today's lesson is on section 7.4, solving linear systems by multiplying first. This section is actually very similar to 7.3, which was solving by adding or subtracting, solving linear systems. Both these sections are talking about the method of elimination. That third one, now that we know, the third one we know how to solve a linear system. They're both talking about trying to eliminate a variable. And as I had in the lesson for section 7.3, here are the things we need to be able to use elimination as our method to solve a linear system. Number one, we need all the variables, the constants, and the equal signs to be lined up. And then two, we need a variable in the system that can be eliminated by adding or subtracting the two equations. As we're going to see in this new section, sometimes we have to do something else to manipulate the equation so that we can still solve it using elimination. So in this problem right here, this example that I've got down below, this one's got everything all lined up for us. The like terms, the terms with x in, the terms with y, the equal signs, the constants, everything's all lined up. This is what we've been working on to use elimination, so this is just a nice basic example. My next one I go through, though, will be one where I'll show us okay, well, what if we don't have something we can eliminate right away? Then we got to do something else. But here, just going through this example to refresh our memory. So what happens in a problem like this? This one is set up right now for elimination. It's got all the terms, all the like terms lined up. And also we've got a variable that we can eliminate by adding or subtracting. In this particular problem, if I subtract my 3x minus 3x will eliminate that variable, the x variable, and then I'll just have y's left, and then that'll allow me to solve this particular system. Now, if you remember from my lesson on section 7.3, I also recommended that whenever you're going to subtract two equations to solve a linear system, instead of actually subtracting and going through and taking 3x minus 3x, negative 2y minus y, 8 minus 5, instead of having to try to remember that you're always subtracting for those, my recommendation is do kind of a chop dash, as I say in class, or I'm going to chop this and make it addition really, but I'm just going to change all the signs of everything in the second equation. And that'll be just like subtracting. In this case, though, then I get to add, which is a little easier. And in case there's a lot of negative signs in there, like I'm minusing a negative number from another negative number, I don't get confused on what ends up actually happening or what I end up getting. And also I don't forget that I'm subtracting. Sometimes I get students who get to like the second or third term and it seems like a small thing, but we've already forgotten that we're supposed to be subtracting the terms, and then we get the wrong answer. So my recommendation is if you're going to subtract, that is good. Know that you're going to subtract the two equations, but instead just end up adding all the terms, but make every term in that equation just the opposite sign of what it is when it starts. So in this case, I've chop dashed everyone, so now it's negative 3x, negative y, and negative 5. This will be a little easier to subtract these. 3x plus negative 3x, again, those are just going to cancel out. So my x terms will be gone. I could write 0x down here, but I really don't need that because 0 times x just gets rid of those. So it'll be just 0. Now I have negative 2y plus negative y. So again, I think that's easier to understand what's going on as opposed to subtracting them. Negative 2y plus negative, again, this is like negative 1y if I want to put the coefficient in there. Then I'm going to get negative 3y. And 8 plus negative 5 gives me 3. So by using elimination, I eliminated the x variables. And now I've just got the y variables here. Negative 3y equals 3. I've got this new equation that I can solve and find out what the y coordinate of this system should be. And if I divide both sides by negative 3, I think I get that y is going to be negative 1. Then I can take that negative 1 and plug it back into either of the equations for y, substitute that back in, and that'll allow me to find my x coordinate. 3x, and then this would be negative 2 times negative 1, which would actually give me positive 2, so it'll give me plus 2 here, equals 8. Subtract 2 from both sides, 3x equals 6. Divide both sides by 3, x equals 2. So the solution for this system ends up being 2, negative 1. Again, just a reminder, so what does that mean? That's the solution. That's the answer. 2, negative 1 is the ordered pair that would work in both of these equations, the one ordered pair that would work for both of them. Or if you graph both those equations, then that's the point where those two lines would intersect. So that first problem was just a little bit of review, just reminding us, well, here's what it looks like when we're going to use elimination. But now what if, like I mentioned, and like it says up here, and I'll show us what does it mean by multiply first to solve a linear system. It says here, what if I can't eliminate a variable by adding or subtracting? Like looking at the system I have right now, I got 3x minus 2y equals 3, and negative x plus y equals 1. So right now, looking at this system, if I try adding or subtracting them together, it's not going to eliminate either of my two variables. And remember, that's what I need for elimination to work for the third method here. Number one, I need everything lined up, and I've got that. But I also need to be able to add or subtract them, and it should eliminate something so that I can then find whatever the other one is and use that to solve. Well, in this case, I don't have that. So elimination is a great method, but it's got to be able to be set up correctly for it to work. However, have no fear. There is a way to set this problem up for elimination still. Like it says for the section title here, solve linear systems by multiplying first. What we can do is we can change one of these equations by multiplying every term in that equation by some factor. And that'll give us an equivalent equation, okay, one that we can also use to help solve this system. So, for example, let's take the second equation. What I'm going to do is I'm going to multiply everything in this second equation by 3. If I do that, what would my new equation be? Well, if I multiply every single term by 3, I'll get negative 3x plus 3y equals 3. Okay? And now that seems like, well, you're totally changing the equation. Why are you able to do that? Like, that seems like now I've just made a brand new equation. Well, no, actually you haven't. These two equations are what we call equivalent equations. And that means they have all the same solutions. And I'll even show you here by bringing a grid up for a second. But just to show that really these, even though I've changed what it looks like, it's really the same set of solutions, the same equation, just manipulated. I'm going to show what the graphs of each of these look like now. So this original equation, here's the first one we had. I'm going to graph that one and we'll see how it compares to the new one. I'm going to use intercepts method. So if I plug in 0 for x, so that would give me a y-intercept of just 1. If I plug in 0 for y, that would give me an x-intercept of negative 1. So I'm going to plot those points, 0, 1, negative 1, 0. Now I'm going to go over to this one, and I'll do it in blue. Actually, going back for 1 second here, I should graph the first one, though. So here's what that one would look like, going through both those 2 points. There's the graph of that first equation, negative x plus y equals 1. Now going back to the second equation, the new one I've made from that one just by multiplying everything by 3. I'm going to graph this one using intercepts method as well. So if I put in 0 for x, what happens? Well, my y-intercept, I'd have 3 divided by 3, which would be 1. And if I put in 0 for y, I'd have 3 divided by negative 3, which would be negative 1. So my intercepts for this equation are 0, 1, and negative 1, 0. What do you know? It's those same 2 points. So if I graph this, yep, it is right on top, if I draw it nicely, right on top of the other equation. So it is the exact same equation. It has all the same set of solutions. It just looks a little different, but that is something you can do in algebra, in mathematics. I can manipulate an equation just by multiplying everything in that equation by some factor. And as long as I do that and stay consistent, then I can change that equation and maybe use it to help me. So I'm going to move this grid out of my way again and go back to our problem and show you again one more time here. Well, I'm going to multiply everything in this equation by 3. So that changes this to negative 3x plus 3y equals 3. Why does this help me? Well, if I multiply everything in that equation by 3, now compare that with the first equation in my linear system. Now I've got something where I can use elimination like we've been doing. I can add these two equations together. 3x plus negative 3x will cancel out all the x terms. I'll have 0 x's, so that's what I want. Now I can use elimination. The x terms are going to cancel out. Negative 2y plus 3y will just give me 1y, so just y by itself. And 3 plus 3 gives me 6. So there we go, I got y equals 6. I can plug that back into one of the equations. I can actually plug it back into the original. I can plug it back into this one. I could even plug it into the new one I made, because remember, I just showed us that one is actually the same as the first equation anyway. It's the same as this one still. So any of those 3 equations I can plug it back into, and it'll still give me the right answer. If I plug it back into that first one, so we'll go to this one over here, the one that I changed. Negative x plus 6 equals 1. Subtract 6 from both sides. I'm going to get negative x equals negative 5. And so if negative x equals negative 5, what does regular x equal? Just regular 5. So I just flip the sign there. So I find out that the answer ends up being 5, 6 for my solution. So even though this system right away wasn't set up for elimination, by multiplying one of the equations first by a factor and just multiplying every single term in that equation by that factor, I can still solve it or set it up for elimination and use that method to solve. I'll show us another example here, just so again we get a better idea of what to do, or start to maybe pick it up now. X plus y equals 2, and then 2x plus 7y equals 9. There's the two equations in my system. Again, right now, if I'm trying to use elimination, I couldn't do it. Okay, there wouldn't be a nice way because, well, I can't add or subtract these together and eliminate one of the variables. So I can't use elimination right now. So we won't do that. But we can set it up for elimination. If I multiply one of these equations by some factor, then maybe I could get it to equal one of the other variables in the second equation, and then I could use elimination. Let's look at that first equation. And if I multiply everything in that equation, let's say by 7, I'm going to try to eliminate the y variables. I want to multiply everything by 7. What is that going to give me? Well, now I'm going to get 7x plus 7y equals 14. Okay. By changing it into that new equation, and again, it's not even, I shouldn't even say new, I guess just to that equivalent equation. Again, it has all the same solutions as the first one, so it is still the same thing. Now, I can use elimination by subtracting these two equations. That'll eliminate the y variable, and then from there I can keep solving this system. So in this case, I'm going to subtract. And again, my suggestion is, though, if you're subtracting, what I would instead do is just actually add, but just change the signs of every term. So now I've got 7x plus negative 2x, which gives me 5x. 7y plus negative 7y, which gives me 0y. So again, there we go. They canceled out. And 14 plus negative 5, which gives me 5. So now I've just got 5x equals 5. And if I divide both sides by 5, I get x equals 1. So good. I'm on my way to solving my system. Again, I can plug this back into any equation, really, or any of the three equations. I can plug it in here. I can plug it in here. I can plug it in here. And every one should give me the same answer. I'm going to do the first one that I wrote to over here because this one looks like the easiest. So if I plug 1 back there, I got 1 plus y equals 2. And subtract 1 from both sides, I'm getting y equals 1. So the solution for this one should be just 1, 1. I'm going to show us one more example, because this new problem, there's one other thing we may see when we're trying to eliminate, when we're trying to use elimination as the method for solving this system. In this system that I got here, 3x minus 7y equals 5, and 5x minus 9y equals negative 5. If you look at these two equations, unlike the other examples I've done so far, there isn't some nice number that I can multiply the top equation by and get numbers from the bottom one, or get like a term that I can eliminate from the bottom one. I could do it, but it'd have to be some kind of fraction like 9/7 or something like 5/3. So, and I could do that, but then it gets a little messy with the fractions. So there's a little easier way though. Since I've shown that, well, when I multiply an equation by some factor and it doesn't change the solutions, we could just do that to both equations in this case and find a least common multiple of one of these sets of variables, like the least common multiple of 3 and 5, or the least common multiple of 9 and 7. And we'll see that that'll still allow us to eliminate. So I can multiply both equations by some number, and that'll allow us to set it up for elimination as well. I'm going to look at 3 and 5. We're going to try to eliminate the x variables. So how would that work? Well, in this case, the least common multiple of 3 and 5 ends up being 15. And so what I would do is I'd multiply the top equation by 5, and I'm going to multiply the bottom equation by 3. And that'll give me, again, two equivalent equations that I can still use to solve this system. They'll be equivalent to the ones that are originally given to me in the problem. So this one, the top equation, will become 15x minus 35y equals 25. The bottom equation becomes 15x minus 27y equals negative 15. And I won't finish the whole problem, but I think you start to see here what could happen is now that I've got x terms that have the same number here, the same coefficient, 15 and 15, well, now I can solve this system by using elimination. I've changed both of them into these new equations, but again, they're equivalent equations. If I graph them with their originals, it's really the same exact set of solutions, the same line. So I can use these to help solve the system too. In this case, we'd subtract. So again, my suggestion is, well, instead of subtracting, I'm going to add. I'm going to change this to negative 15x. In this case, I'll change this to plus or positive 27y. And this one also change into positive 15. And now I'm just going to add all the like terms to combine. So 15x plus negative 15x cancels those out. Negative 35y plus 27y is going to give me negative 8y. I had to think for a second there. And then 25 plus 15 is going to give me 40. And now if I divide both sides by negative 8, I can get y equals negative 5. And I can plug that back in and to any of those equations and find the solution to my system. But showing that sometimes elimination, just like substitution, these two methods, sometimes we have to set the equations up so that we can use them. And elimination, similar to substitution. Sometimes I might even have to multiply. Sometimes I have to multiply both equations by something, by some factor, or one of the equations. But as soon as I get it set up, it is a pretty nice way to solve a linear system.